Myself Raki Kumari, Assistant Professor in the Department of Electronics and Communication Engineering, ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University. Today in the lecture series of Microwave and Radar Engineering, we will study two-cavity klystron. Till now what we have studied? Till now we have studied about the microwave frequencies, microwave waveguides and other microwave passive components. And in the last lecture, we have done with the problem faced by the normal vacuum tubes at the microwave frequency. So, if the normal vacuum tubes does not properly work at the microwave frequency, so the new types of components come into the existence for the microwave frequency. One and the foremost important of that is the two-cavity klystron. So, what is the two-cavity klystron? The two-cavity klystron is a widely used microwave amplifier, which are operated by the principle of velocity and current modulation. Till now, being a student of communication engineering, you have studied about the different type of modulation techniques. For example, amplitude modulation, phase modulation, frequency modulation. So, but this velocity modulation concept come into the existence for the first time for you, and that in the case of a microwave two-cavity klystron. So, what are the basic components which are associated with the two-cavity klystron? First one is the electron gun, focusing and accelerating grids, two identical cavities separated by a distance and the far end grounded collector plate. So, these are the basic components which are with two cavity klystron. So, what is the function of a electron gun? So, the electron gun emits electron from the surface of its cathode and then they are focused into the beam, and which part does the focusing of the beam? That is our two identical focusing and accelerating grids. Now, after that a DC accelerating positive voltage, the beam is accelerated to high velocity. So, there the velocity change occurs, that is why the velocity modulation is the basic principle. Now, the characteristic of a two cavity klystron: efficiency, it is about 40%, power output in continuous wave mode up to 500 kilowatt at 10 gigahertz, power output in pulsed mode up to 30 megawatt at 10 gigahertz, and power gain is about 30 dB. Now, here comes the schematic diagram of a two cavity klystron. So, the two cavity klystron consists of this one first, that is the cathode which emit the electrons and electron guns are with it. Then it is converted into proper beam with the help of this grid which act as an anode also. Now, this is the two cavity, first one is the buncher cavity and second one is the catcher cavity. They are basically identical to each other and they are separated by a fixed distance L. And again we are talking about one type sort of collector. So, this is the collector. What is going to happen in this? That the frequency which we have to amplify, the RF input is the signal which we have to amplify with the help of a two cavity klystron. So, this is the input which has to be amplified and this is the biasing input. So, and this is always greater than this input. We always keep in mind that V naught is always greater than the RF input signal which has to be amplified. So, what is going to happen? Electron moves from here with a velocity, initial velocity of V naught, and when in between it comes across the buncher cavity, and in the buncher cavity it get interacted with the RF input signal also, which is inserted inside the two cavity klystron with the help of buncher cavity. And after coming out of it, what is going to happen? The velocity of electron does not remain the same, it changes into the modulated one, that is the VT1. And now, what is going to happen? So, in the modulation case, the electron are in the form of a bunch And now what is going to happen, that this modulated velocity, of course velocity v is associated with it. So kinetic energy, which is our half mv square, v square, that is velocity square, so modulated velocity square. So kinetic energy of the electron beam increases. So what is going to happen, this electron give its kinetic energy to the RF input signal. When this energy is transferred into the signal, which is at the low intensity, low amplitude, what is going to happen, that its intensity increases, that means it get amplified. So the signal now which is coming here is the amplified output of the signal which is initially inserted in the buncher cavity, and this signal goes out, this RF output, which is the amplified output, basically comes out with this node, and the electron which are now left with without energy are get collected at this collector end. So these are the basic principle which is associated with the two cavity klystron. So the velocity modulation plays a very important role because it increases the velocity of the electrons associated with the two cavity klystron, and in turn it increases the kinetic energy. Now the electron is having the more kinetic energy and it transferred its kinetic energy to the RF input signal, and the RF input signal get amplified and it comes out with the this node from the catcher cavity, and the electron which is now without the energy is get collected here. So these are the working of a two cavity klystron. Now again just the recap of that. Cathode, what is the cathode? The source of electron. Anode, for the formation of electron beam. Buncher cavity, basically it is the entrant type cavity which is kept at the positive voltage of V0 with respect to cathode to affect acceleration. We will discuss about how the velocity modulation is done in the next slides. RF input voltage of V1 sin omega t is applied to the buncher cavity. Similar, catcher cavity, it is similar to the buncher cavity. The amplified output signal, that is V2 sin omega t, is obtained from this cavity. And again the collector function is that electrons after transfer of energy to the catcher cavity, so that the signal are amplified, are collected at the collector. These are the working of a two cavity klystron. Now the process of the velocity modulation. So when electron are first accelerated by the high DC voltage V0, which we have seen in the figure, electron are accelerated by this V0. In that case, the velocity associated with the electrons are V0 is equal to 2 under root 2 e V0 upon m. And when we substitute the value of E and m and take the under root of that, we will have this value as, and of course we do not know the value of the V0 here. So the under root V0, and the velocity unit is meter per second. Now the microwave signal which has to be amplified is inserted inside the two cavity klystron to the buncher cavity, and it is when a microwave signal is applied to the input terminal, the gap voltage between the buncher cavity appears as this one. Now this V1 is the amplitude of the signal, and V1 is very less than V0, because that's why we say that we have to amplify it. Now since V0 is very less than V0, the average transient time to the buncher gap distance d is given by tau is equal to d upon V0. So what is d here? D is the buncher gap distance. You can able to see this in this figure also, this one, buncher gap distance. Here it is 0 and now it is d. So the total distance is d here, and it is given by T1 minus T0. T1 is the time at which the electrons leave the buncher cavity, and the T1 is the time at which the electron leaves the buncher cavity, and T0 is the time at which the electrons enters the buncher cavity. Now when we have the average gap transit time, what we are going to do? We are multiplying the tau with omega, and this is represented as theta g. So, when we multiply tau with omega, it is the whole expression of the tau is multiplied with omega, omega T1 minus T naught and omega d upon V naughts. So, in the last what expression which we have seen in the last slide is overall multiplied with omega, and that is represented by theta g. Now, the average microwave voltage in the Buncher gap can be found by this average. That is why we have taken the tau at the denominator side, limit T naught to T1 because we are talking about the Buncher cavity, and Buncher cavity transit time is T naught to T1. Frequency, signal amplitude V1 sin omega t. Now, when we integrate it with the limit T naught and T1, we are able to get this because sin omega t give cos omega t, minus of cos omega t, that is why minus come here, and when we put the limit, we will have this one. Now, what we are going to do here? We are to change this minus sign, we are keeping this as the first term and this one as the next term, and we are replacing omega T1 with the next one, this term. You can able to see this, omega T1 minus omega T naught is equal to omega d upon V naught. So, at the place of omega T1 we can write omega T naught plus omega d upon V naught. This is the simple thing which we have done here. Now, we have to solve this equation. So, the next step which we are going to do is just the step which we use for solving the equation. We are representing omega T naught plus omega d by 2 V naught as A. Theta g is here because we have already taken omega d by V naught as theta g. So, this term can be represented as A. Now, omega d by 2 V naught is equal to theta g by 2 and it is represented as B. So, this expression what we can have to say that this is the omega T naught. So, we can say that this is V naught upon omega tau and this is cos A minus B, because this is A is omega T naught plus theta g by 2 and B is theta g by 2. So, when we take A minus B, we are left with omega T naught only. So, the first expression is omega cos A minus B, and this one, this is omega T naught plus theta g by 2 and B is theta g by 2. So, we can have it cos A plus B, and when we solve cos A minus B plus cos A plus B, what we are getting? 2 sin A sin B, and this term remains the same. So, that is the expression which is written here now. V1 sin omega d by 2 V naught upon omega d upon 2 V naught sin omega T naught plus omega d by V naught. If you are able to solve this equations, then only you are able to get this final expression. Cos A minus B plus cos A plus B give 2 sin A into sin B. This is the normal general trigonometric equation. Now, what we are having now? Omega d upon 2 V naught is our theta g by 2. So, we are replacing here, same here theta g by 2, this one, where this is represented as beta I, and this is the beam coupling coefficient of the input cavity gap. And what we are interpretation which we are getting out of this, that it will be seen that increasing the gap transit angle theta g, that increasing this angle decreases the coupling coefficient because it is on the denominator side. So, if we increase this, of course, we are able to what we are increasing the decrease the coupling between the electron beam and the catcher cavity. The velocity modulation of the beam for given microwave signal is decreased. So, we have not to increase the transit gap angle. Now, after the velocity modulation, what we are getting? Vt1, which is the velocity after the velocity modulation, and it is given by 2e upon m v naught. This is the initial velocity, and now the amplified one is added with this. This one is the amplified one, and it is added with this, and we are able to get this as the final equation on solving, where the factor beta I upon v naught into v1 is called the depth of the velocity modulation. And if we write it more precisely, we can have it, we know that v naught is equal to 2e v naught upon m. So, at the place of this, we can simply write v naught, and this will be, of course, the expression will be half, since it is a under root. Now, by the binomial expansion, we will do the binomials expression, and after that discarding the higher order function, the final equation which we are getting is this one. This is the final equation after the velocity modulation by doing the binomial expansion and discarding the higher order, and only taken the minimum order frequency signals. Now, the bunching process. When the electrons leave the buncher cavity, they drift with the velocity given by Vt1, which is our modulated velocity. And now, how this forms the bunch of the electron. The effect of velocity modulation leads to bunching process and the current modulation. So, what is going to happen now here? What is going to happen? That some velocity are leaving the buncher cavity with the same velocity, and some with the decreased velocity, and some with the faster velocity. But the signal which are with the slower velocity are at the will come first at the time t equal to 0, and it will be later. So, what will going to happen? This will reach the destination at the same time, and when they reach the destination at the same time, they form the bunch of the electron. So, these are the reason that means ki some electrons had the decreased velocity, some electrons have the increased velocity, and some have the same velocity as the initial. So, that is why it is going to happen. For the distance, when from the buncher grid to the location of the dense electron bunching for the electron at Tb, Tb means at the same velocity. So, for that one, del L should be equal to V naught Td minus Tb. Td is the time at reaching the final destination. Now, for the other two one, which is the slower and the other one is the faster. For the slower one, distance will be remains the same, distance will not change, but the velocity is going to change. It is travelling with the minimum velocity, and with the time duration Td minus Ta. Ta is the time at which the slower moving electrons leaves the buncher cavity, and Td is the time at which it reaches the final destination. Similarly, for the faster, Vmax Td minus Tc is equal to what is now going to happen? V min Td minus, we have to relate Ta with the Tb. So, what is the relation between Ta and the Tb? That is, it is Ta is equal to Tb minus pi by 2 omega, because it is the lesser time, and here Tc is equal to Tb plus pi by 2 omega. So, we are having this equation. So, now minimum velocity and the maximum velocity is given by V naught V1 minus beta I, which is our depth of the modulation, with the bunching parameter over 1 plus beta I upon V1 upon 2 V naught is the Vmax. So, in the next step we are going to substitute this Vmin in this equation and this Vmax in second equation. So, on substitution what we are getting, all the students please substitute the value, then only you are able to get this value. And on substituting Vmax value we are able to get this. So, the necessary condition for this electron Ta, Tb and Tc to meet the same states del L, what is going to happen? We are, this one is the same. So, the deciding parameter is this one and this one. So, this one on the subtraction should give the resultant as the 0 and we are just doing that. So, at the final destination on doing this, what we are getting? We are getting Td minus Tb is equal to pi V naught upon omega beta I V1, and when we substitute this we are able to get the final del L. Now, since the drift region is field free, the transit time of an electron to travel a distance L is given by T2 minus T1. The drift distance is the T2 minus T1. So, if you want to look at the drift distance, you can able to see it. This is the drift space after leaving the buncher cavity till it reaches the catcher cavity, so that it can be go outside is the our drift space. So, at this time transit time of electron travel distance L is our T2 minus T1 and it is basically given by L upon our modulated velocity. And when we substitute the final expression of that, we are able to get this expression. In the terms of radians, what we are going to do? This T is multiplied with omega and the final expression we are getting like this, where theta naught is omega L upon V naught, which is equal to 2 pi n, is the DC transit angle between the cavity, n is the number of electron transit cycle in the drift space, and x is given by beta I V1 upon 2 V naught theta naught, and this x is our bunching parameter of the electron. Now, we have to actually go through the current. What will the current equation? So, at the buncher gap, a charge dq naught passing through a time interval dt naught is given by, because q is equal to it, so I naught dt naught, and from the principle of conservation of charges, this same amount of charge dq naught also passes the catcher at the latter time interval dt. So, I naught dt naught should be equal to I2 dt2. So, this principle of conservation of charge can be achieved, and after that we are able to get the I2 at the time t naught, and it is given by this equation, and I2 at the time t2 and it is given by this equation. And finally, the efficiency of the klystron. The efficiency of the klystron is given by P out upon P in. On substituting the value of P out upon P in, we are able to get the efficiency of the two cavity klystron. So, the important formulas which you have to remember is, the first one is this one, which you have to always remember, our bunching parameter, our the equation of the del L, our velocity modulated signals. These are the important parameters which you have always remember, because numerical based on this formulas also come. And when we talk about the what type of questions comes in this process, basically sometimes it comes to explain the velocity modulation process, explain bunching process, and of course the work construction and the working of a two cavity klystron. So, these are the basic thing which comes in this chapter and within this topic. Let us do now one numerical based on this. A two cavity klystron amplifier is given where V naught is equal to 1000 volt, R naught is equal to 40 kilo ohm, I naught is equal to 25 milliampere, F is equal to 3 gigahertz. Gap spacing in either cavity is given by this, spacing between the two cavities is equal to this, and effective shunt impedance 30 kilo ohm. Find the what you have to find? You have to find the input gap voltage to give maximum voltage V2, voltage gain and the efficiency of the amplifier. So, what we are going to do first? First we have to find out the input gap voltage for the to give maximum voltage V0. So, we go through the for maximum V2 Z1x must be maximum. This means Z1x is equal to 0.582 at x is equal to 1.841. You have to remember this value because sometimes it does not comes in the questions also. You have to remember because this is the condition at which we will able to achieve the maximum. So, V0 is equal to this. So, using the formula only we can able to find this, and now transit gap again we are just using the formula omega d upon V0 and it is equal to 1 radian. Beam coupling coefficient again we are just using the formula, we are able to get it 0.958, and the DC transit angle between the cavity theta naught is equal to omega T naught equal to omega L upon V naught, and we will achieve 40 radian. Now, by getting all this value, we substitute for getting the maximum V1 input voltage. This is the formula which you have to remember, 2 V0 into x beta I theta naught, and then substituting the value which we have obtained, we are able to get the maximum input voltage as 96.5, and this is the equation for the voltage gain which you have to remember the formula for this, and just substituting the value because already all values are either calculated or given in the numerical itself. We are able to get the voltage gain as this one. Now, the last one is the efficiency. The efficiency formula is this one, and I think we are not with the I2 and the V2 here. So, we have to find out the I2 and the V2 using the above formula. Just note it down and try to remember it, because without remembering this formula you can't able to solve this type of question. So, at last we are getting the efficiency as 46.2%, which is which we have already told that efficiency of the two cavity klystron is around 40%. So, here comes the end of our two cavity klystron. In the next lecture we will have the other type of klystron, that is the reflex klystron.